Professor Markus Reuter von der SMS Group wird uns das sehr wichtige Thema Circular Economy, Keeping Valuable Materials in the Cycle bringen. Und ich muss ja sagen, wir haben bis jetzt eigentlich unglaublich geaßt mit Materialien. Es wird viel zu viel weggeworfen bei uns. Ich war gestern drüben in der Glasindustrie. Auch dort ist es so, dass viel von dem Flachglas immer noch nicht gesammelt und wiederverwertet wird. Professor Michael Braungart ist ein guter Freund von mir, der das Thema Cradle to Cradle treibt. Also zünden Sie unsere Zuhörer bitte an mit dem Thema der Circular Economy. Herzlichen Dank, dass Sie gekommen sind. The floor is yours.
So, good afternoon, ladies and gentlemen. Thanks for being here over lunchtime. As it was announced a moment ago, bringing materials back into the cycle is most certainly a very important aspect of our society. And I'd like very much to color this in with the example you see at the back, which is PVs. But permit me also then to weave into this hydrogen, decarbonization, and also what we do at SMS as an example. Our stand is just around the corner at the back if you want to chat after lunch or after the talk. So, having been around for some time, and also being an academic half of my career, and also having grown up in South Africa, you always have to go back and see what has been done. Now, if you read that article that was written already in 1975, explaining in that article, and I can really suggest you would go into it. Then I asked myself, what's new? What are we doing now which we haven't thought about in the past? So this specifically focusing on the non-ferrous industry, how you can use hydrogen, for instance, after the oil shock in 73, obviously. So it's obviously a busy slide, but if you look through this, you'll see all the words we are probably using today: water, circularity, benign, not affecting the environment, etc. It's all there. So I would always recommend, and that's what I say sometimes also to students, go and read the stuff in the past. You'll be surprised what is already there and has been discussed. So Tanaka et al. At the time in Japan looked at this in fair detail of using hydrogen, not only as a fuel, but also as a reductant. And I will come back to that a bit later, because that is stuff we also do at SMS, which is a very large OEM, original equipment manufacturer for steel technology, but also for copper and non-ferrous. I'll obviously be focusing more non-ferrous, which is my career. As I said, I'd like first to define what is circularity in the real sense, because there's a lot of hand-waving going on, and sometimes disconcerting hand-waving. The beauty of it connects a lot of things from the mind to the product and its recycle collection and everything that goes with it. And sometimes little bits and pieces are taken out and put up in the high sort of banner that will save all and will get all the metals back. But you know, one thing that always bothers me is that people never really look at the true losses from that system. Not only the material losses, but also the thermodynamic losses from that system. And excuse me for being academic, but if I speak about circularity, it's never without thermodynamics in the background. And not only the first law, but the second law specifically. What are the dissipative losses which you really can't return back into the cycle? And you see those things beautifully in this figure for PV cells that explain. Not only are you speaking about material losses, but material losses have got an enthalpy, so it's kilowatt. Entropy is a dissipative second law loss. It's got the unit kilowatt hour per hour. And if you don't take that together, you don't really understand what's going on. By just saying design for recycling is great, or we can close the loop, but I always say that's the Excel mafia trying to close the loop on an Excel sheet. But in fact, if you really want to understand this, you need to go to the detail that we, for instance, at SMS do when we design a plant and actually offer a solution that closes that loop. What I always then also try to explain, and this has a long history, this wheel, we call it the metal wheel, which explains quite simply the following. And you know, in the specific times at the moment, one can really recognize the importance of this. You need a base metal industry in society. You need to be able to produce steel, copper, zinc, lead, nickel, etc. That's the inner circle. And if you don't have that, you can't recycle. Whatever you think and whatever hand waving you do, you can't recover the metals back at the quality that is required by the products. And have a look at this drawing at your own leisure in publications which we've done. But just as a summary, you need at the heart of any system in a region, be it Germany or EU or wherever, you need the metallurgy to do this. And economically, by the way. So the policy sort of implication of this was the following, and this figure specifically had the intent to inform, among others, the EU and policy. Removing any sector from that system crashes the system, like this figure shows. So we wrote a policy brief on this, and it's showing that you need the metal wheel with all its complexity to do this. To airbrush it and make it all simple and say it's all too difficult is just impossible. You need it. And we as metallurgists know how to deal with this. And that's why I, as in my long career, it's close to 40 years, I've always tried to protect the sort of metallurgical infrastructure as the key enabler for circularity. If you can't bring the metals back, you're just hand waving. It's nice ideas, nice reports, nice stuff. So that brings me to the next sheet, that there's a lot of nice reports always appearing on criticality of materials, elements. And I say, well, guys, if we don't have the infrastructure to actually produce the metals, everything's critical. And we see that at the moment. But we are merely writing these nice reports which explain all of this, how critical things are. But then I say, well, get the plants to do actually the recycling. So this is meant as a provocative question, so if you have a question, but later on. So coming back to a brief, and I was told very clearly not to do any sort of sales talk here. So I've kept it purposefully down to some physics as well. So here's a nice example from our company, SMS, which is building this e-waste recycling plant in the US. It's the first greenfields plant that has been built in a long time in the US by a German company, Aurubis, which is situated in Hamburg. It's actually trying to bring this together, bringing e-waste, which contains many elements, back into the cycle with the whole and refining infrastructure of the metallurgical industry. So a very interesting example. We're just in the process of sort of designing this very interesting project, and obviously also processing a fair number of and tonnages of material. Here's another one. This is copper recycling, also in the US, in this case in North Carolina, and just actually doing this. So what I'm saying now, it's not just hand waving, it's happening. And it should happen at various places in the world, and most certainly also in Europe. So let me get back to some theory once again. And the previous talk was speaking about AI and big data. You know, I did my PhD on AI 30 years ago. We tried to apply it in our industry, and it's now obviously mainstream. But if you want to understand the big systems, you cannot use Excel sheets. You cannot just do some simple flows of materials. You need to understand the physics. And so here we just show what we do also internally in SMS. We bring these tools together to design plans. And so once again, it's not just theory, it's practice to do this. And obviously then bringing together the sustainability goals if you can. So an example, and once again, perhaps too complex figure for this venue. Here we're trying to understand our different plants that we're supplying as technology and understanding what is the true efficiency if I use hydrogen, ammonia as fuel, or as reductant, or methane, and what is the best configuration. This is true decarbonization. You're trying to understand the system, how best you can connect systems to produce copper in the most green way as you can. But you need the physics to do that, to get that. And ultimately, if you look at the blue box there, you then can understand the exegetic true efficiency of that system. And that's what makes a system profitable in the end. So if you're designing a plant, you need to know this information. And the clients are actually asking this information from us. So, by the way, there it is. So we can do this. And it's not just academic, it's actually happening in the company I work for, which is a very prominent technology provider globally. Once again, we spoke about digitalization. If you want to really understand that true performance of the system, you need to know where the elements go. I'm always so surprised that people are talking in the circular economy environment and they sort of look at elements individually. You can't do that. You have to look at them at the same time. And here's a digital tool that we use to predict the copper quality after the smelter, which I showed previously. For instance, the one we're building in the US. So this is real. And so if you do circularity, you need to know where the tin goes, the nickel, etc., which are all associated with the scrap. And so that is our daily business. And also, I'm not going to explain this at all. I'm just trying to show with this, you need to understand the physics. So let me go to a final concrete example, just to make this clear. And this is all about decarbonization. We speak about PVs. So I was involved also in the Helmholtz organization in this country. One of the projects was to look at the efficiency of PVs, not only from the material science point of view, but from the system perspective as well. So what is the true recyclability, the circular economy of PVs? So here are, I would call them minerals or design or whatever you'd like to call them, that provide this efficiency between PERC cells to tandem cells on the right-hand side. But you can see they are pretty complex. And trying to understand the circularity of these is not that easy. So, once again, a busy slide, but don't look at the detail. If I'm creating that PERC cell and I'm recycling it in the circular economy, you need all those plants. That's the detail. And then I'm always dumbfounded how things are simplified to nonsensical results in the end. But in the end, this is what you need. This is the material flowing in, you design the product, you manufacture the product, and you bring it back into the cycle. Exactly that circular economy picture that I showed earlier. So this figure here, bringing the bits together, this is what you need to do. And so I can give you this nice circular economy is going to save the world talk, and I can recycle everything infinitely. That's utter nonsense. And this figure, you once again see the dissipative losses from the system, which we can quantify. They cost money. They make the system work or break wherever it is done in the world. So, some results, and I've simplified this in a simple figure that just shows the normal sort of simplification that is used to make it tangible to policy people. But just as a summary, the material flows in, it's recycled, it's linked also to the perovskite type cells, brought together and recycled. So let's just quickly look at some results, and you can see this all in the academic literature. So this is all peer reviewed. We've done this over the last 3-4 years. So if you have this nice big model, you saw all those plants, then you can precisely, well not precisely, but within the framework of those models, calculate the recovery of elements. You can estimate the economics of it. If it doesn't work economically, you can forget it. And this is what this figure shows. And it also shows that you don't just recover elements, you recover compounds, you produce compounds, you produce alloys, high quality alloys that they can go back into the product. So one of the other statements that I always make also to students, also here now, true circularity would mean the copper that I have in my mobile phone goes back to that mobile phone. That is circularity. If I'm talking about design for recycling, if I'm talking about closed loop, I'm not speaking about open loop, closed loop, you need to understand that. And I'll get to that in my last slides. So what can you get out of this once you have this structure? And we've created all the software platform to do this. I teach this to students in block courses. So nobody can tell to me this is all too difficult because they've not been trained in it. But ultimately, you then can very simply get scope 1, scope 2, and scope 3 for looking at the effect of recycling rate on the carbon emission and all the other emissions. Please note, we have created the software over the last 10 years to do this. Also through the industry side, not through academic industry side, to actually help industry to footprint processes that have not yet been developed, that are not in the LCA databases, to actually footprint them and provide information to clients if that is so required. But here you can see for the different cell types what the results are. And once again at the bottom you can see that these references are there. So what can you do with this? Remember that big flow sheet that I showed with all those reactors? If I would place them in different regions of the world, and I would look at the effect of recycling rate on the carbon footprint, you can clearly see that one should start thinking of, if I'm using green tech, the metals must also be green, as shown over here. And that's not always the case. Otherwise, we're just hand-waving. Then ultimately as well, this discussion of everything must be recycled. And this figure shows it, the lifetime cost energy generated on the right-hand side. In this case, for a tandem cell, as a function of recycling rates, there's an optimum between the two. You can't just say, oh, we want to recycle 100%. There's some economic optimum between those. And you have to understand that to obviously maximize that system. So closer to home, some work we've also done just to show, once again, coming back to technology. So this is not just nice sort of talk here. Here's a typical flow sheet of a copper production. Your copper that you're using in these wires, we've looked at systems like this. How can we integrate hydrogen into that flow sheet? And what's the economics of that? And it's not just about copper, it's about all the other elements that are also created. So in this case, it's copper concentrate being produced, being processed to copper product. So you can use hydrogen in various ways as a fuel and as a reductant. Exactly what was said in 1975 already, so many years ago. It's being once again done again. But it's all been tested over the years. In my whole career, I've seen it so many times that the things have already been applied. So what do you want to look ultimately at? What's the economics of this? Must the carbon price be for which type of electrolyzer, be it a PEM or a solid electrolyte system or alkaline system? Where is the economics of that? And here's a very nice graph that actually shows this in the publication that is listed at the bottom. A PhD student that just graduated about 2-3 months ago on this. But you can read this in the scientific literature as well. So let me just end off, Chairperson. Once again, I looked at this bigger picture of the circularity. One thing that has obviously also always floated is design for recycling is going to be the savior of all things. There's one company that has always been brutally honest, and this is Fairphone. And I've been working with them for close to 5-6 years now. Here's the Fairphone 3, and they just wanted to know what's the recycling rate, the true recycling rate. And so we put this all in a pretty large model in about 2016, around there. Here it is, it's real. So what is the result? You can, as I said, you can read it in their report. And we tried to float the recycling label. It's not been taken up yet. Fact of the matter is, and this is on their webpage, is that their recycling rate of Fairphone 2 is what's shown over there, about 30 to 40%. And they've changed the design according to what the first simulation was, true design for recycling, to get it to that level that it's now for Fairphone 3. And so this, we can recycling a mobile phone 80%, 90%. Once again, nonsense. Circularity means I take the Fairphone and I get that metal to the quality that goes back into that Fairphone. And just as I'm speaking about circularity, that's what this is about. And that's not so easy to do. I always say, if I take my cup of coffee yesterday and I try to make the same quality cup of coffee from yesterday's stale coffee today, you would immediately understand it's virtually impossible to do economically or even in the real world. So in conclusion, circularity, what I try to show is this connected of the different aspects. I cannot show everything. What I also try to show is that all units in that circular economy can be quantified as kilowatt. The energy flow, like we did in the PV set, created by the system. The material flow as an entropy as kilowatt. The entropy loss as kilowatt. No fuzzy factors, just physics. And we need to do that. And so I had this very interesting interview with Arubis, where we actually discussed this. And the industry is also discussing this. What is the true limit of this stuff? Arubis, as I said earlier in the talk, is the plant we are building in the US for e-waste recycling for this company. So the inconvenient truth is the figure on the left-hand side, which shows that you have all these losses. So it's interesting as well, the Journal of Sustainable Metallurgy actually has that figure as their leitmotif of their journal. Just to show, this is what sustainable metallurgy, sustainability is truly about. It's in the end about physics, not nice talk. Okay, so I leave you with that talk, and we've also just finishing a Handbook of Recycling. A lot of this information, the second edition, is now going to be published. Hopefully we have the book ready in end of the year or early next week, early next year. So thank you for the opportunity to talk and be here with you this afternoon. Thank you.
Thank you, Markus, and thank you that you have the courage to talk about inconvenient truths. And as I'm a publisher, I would like to have an article from you, because I think we need a much more systemic approach for closing the loop. And if we don't do this systemic approach, we have no chance to really have a circular economy. Is that right?
You've actually captured, in other words, my talk.
Okay.
You need to have an overview, but without forgetting that your feet are on the ground, which is governed by physics.
So who is responsible to make the systemic solutions to happen? Is it politics? Is it companies? How can we bring the different players from different industries together?
As I showed as well, inside SMS, we're actually doing this. So from the company side, we need to understand the processes in this way. From the other side, if I still have a hat of as an honorary professor, so I give a block course of 80 hours where I teach young people how to do it. And you'll be surprised at how many people come. So I think bottom up will help a lot to actually start pushing it and hey guys, are you talking sense or not? So I don't know, I'm burning the candle from both sides.
Perfect. Thank you very much for pushing and for really motivating young people to have a look at this. Are there any questions from the audience? I would be happy if you use this incredible opportunity to give your questions to Markus.
Thank you, Markus, for this very fine presentation. I think the definitely finite element in the world is phosphorus. Could you talk a little bit about the circular economy of phosphorus? Is this SMS dealing in this way?
Oh, that's a nice question, because that takes me back to my past as well. There were 3 beautiful submerged dark furnaces, 60 megawatt in the south of Holland, producing thermal phosphorus. They were closed. So once again, answering your question, you need obviously to understand the furnaces. You'll have to have the technology to do this, but they were closed. So that's really what I'm trying to mention here. If you don't have that infrastructure, we can have nice theoretical discussions, but they get us nowhere. So looking at phosphorus as well, when we are having our design models, we have to obviously look at all the elements. The client wants to know where they go. That means one has to know the physics in each reactor where the phosphorus would go, and depending on the type of reactor and what is inside, say, the residue, you may have the chance to channel it into a direction where you then can economically recover it. But yeah, I had a PhD student in 2010 at Delft when I was full-time professor that addressed the physics inside these furnaces, and I was so unhappy. I was already in Australia at the time when I heard they closed them. And that's unforgivable.
It is incredible. All the solutions are here. And I again say, we have brilliant scientists, we have brilliant engineers, but the lack is politicians, marketing people, CEOs, people who only look at the profit of things, and this is really the ruin of our world, I think, and that's what we have to change, and what would be quite easy to change. But as long as companies want to have an ROI, a return of an investment within 3 years, instead of having the patience to wait for 6 or 7 years, then we could do a hell lot of investments that would really help to save our beautiful planet. So thank you, Markus, for your engagement, for your activities. Please, let's use my favorite SDG, and my favorite SDG is number 17, and number 17 of the SDGs is all about cooperation. If we want to close these loops, it's important that we have a new attitude to cooperation, to look over frontiers, to go into other industries. So I'm looking forward to talk to you, and let's join our forces. Thank you very much for coming.
Pleasure.